Hi there, Mr. Sutton here, bringing you the BC Calculus 8.5 Extra Practice number 3 solutions on polar functions, slope, and basic area. For this one, we want to know the slope of the line tangent to the polar curve r equals 3 theta at the point where theta equals pi over 2. Okay, so we basically need to come up with an expression for dy over dx, and then we need to plug in pi over 2 for all the thetas that are involved in that. So to do this, I have to first express this curve parametrically in terms with x and y, and then I'll put that together to get a dy over dx. So let me start by expressing an x function for this. So we know that if this is your polar curve here, then x is going to equal r times the cosine of theta. So that's going to be 3 theta times cosine of theta. So now I need to take x prime of theta, so I can use that for my dy over dx later on. But that's going to require the product rule here. So let me set up the box and ribbon. We have 3 theta and cosine of theta, and the derivatives of those are 3 and negative sine of theta. Using the ribbon to multiply that out, we have 3 cosine of theta minus 3 theta sine of theta. And now we move on to talk about y of theta. That's just going to be r times the sine of theta. So 3 theta sine of theta. This is another product rule if you're taking the derivative. So box and ribbon time again. Now we have a 3 theta again, but now we have a sine of theta. This is a little bit different. So we have 3 and cosine of theta for the derivatives. So this comes out to 3 sine of theta plus 3 theta cosine of theta. Now to do dy over dx, evaluated at theta equals pi over 2, I'm basically doing y prime of pi over 2 over x prime of pi over 2. So this is going to be, let's see here, y prime of pi over 2, that's going to be pi over 2 plugged into this thing. So 3 sine pi over 2 plus 3 pi over 2 cosine of pi over 2, all that stuff. Now we're dividing by x prime of pi over 2. So 3 cosine of pi over 2 minus 3 pi over 2 sine of pi over 2. It all kind of looks the same to me, but I'm copying and pasting very carefully here. So going through now, sine of pi over 2 is really 1. So 3 times 1 is just 3 up there. Plus, now we have all this stuff over here. Cosine of pi over 2 is 0, so that whole second term gets zeroed out, thankfully. Down here, we have another cosine of pi over 2, which we just said is 0. And we have sine of pi over 2, that's 1. Being multiplied by all this is going to give us negative 3 pi over 2. So if this were a free response, I could actually just leave the answer like this. Actually, I could have stopped back here, because even with trig functions involved, as long as you're plugging constants in, it's considered a constant. But I have to simplify to get one of these answer choices. So this is really 3 over negative 3 pi over 2. Multiplying by the reciprocal, we've actually got 3 times 2 over 3 pi, and all that's negative. So negative 6 over 3 pi, which I can then reduce to negative 2 over pi. So that's answer choice B. For this one, we have a polar curve defined by r equals theta to the k plus 2 theta squared plus 1, and k is some unknown positive constant, which of course we're going to have to solve for that later. We want to know for what value of k will the instantaneous rate of change of r at theta equals pi come out to 15. So basically here, we need to take the derivative of r with respect to theta, plug in pi, and then set all that equal to 15, and we'll still have a k kicking around in there that we can then solve for. And we're allowed to use the calculator, as you can see by the answer choices. So let's start by taking the derivative of r, treating k as a constant. This is going to be a power rule, so this is going to be k times theta to the k minus 1. And over here, this is going to be, let's see here, 4 theta to the first power. And that 1 is just a constant, so that goes away. So I want to find out if I plug in pi for theta, so r prime of pi, so k times pi to the k minus 1 plus 4 times pi, if I do all that, what value of k makes all of this equal 15? And this is something that I can now solve on my graphing calculator. So to actually do this on the calculator, I went into my y equals, and I'm basically treating this k as a variable at this point. I'm calling this k x. So I wrote x times pi to the x minus 1 plus 4 pi. That's going to be my y1. For y2, I put the other half of this equation, 15, and I'm just going to figure out where these two things intersect. That's going to be my k value. Now, I do need to have some kind of window to graph this in. looking at my answer choices for possible k values, it looks like if there is any such k that works, it's clustered somewhere between 1 and 2. So I'm going to make those my window there. So I'll go to Window, X min I'm going to use 1, Y min I'm going to use 2, or X max rather, I'm going to use 2, Y min we don't care about. X max is 2. Let's do zoom 0, zoom fit, and let's hope we see some kind of intersection. So there is the left half of my equation, this k pi to the k minus 1 plus 4 pi. There's the 15 cutting through, and we do see an intersection. We do. Let me do second trace 5 for intersect. And let me just move my spider here, press enter 1, 2, 3 times, and that comes out to exactly 1.451. So there was my picture, there's my value, and that's my k value, which gives me answer choice B. For this problem, I'm trying to find the area of one petal of this rose whose curve is r equals sine of 7 theta. So I have an area formula, but in order to use it, I need limits of integration. I need to find out basically what angle this petal starts at and what angle it ends at. So to figure that out, let me just set my r value equal to 0, because the beginning and the end of this petal happens at the pole, and the pole is the place where r equals 0. So if I set sine of 7 theta equal to 0, I'm actually going to solve that on the calculator. To do this in the calculator, I've entered my r function as a y function. I have y1 equals sine of 7x, and I'm going to go ahead and graph this and see where it hits the x-axis, the input axis, I guess, and that'll correspond to this angle here. So let me get a good window on this one. I'm thinking I'm just going to look in the first quadrant here because I see multiple places where this function has a radius of 0 in that first quadrant. So for my window, let me go from 0 over to pi over 2. And if I need to expand my window, I will, but I think this is a good starting place. So let me now do zoom 0, zoom fit, and let's see what this looks like. So there it is. We have a few crossings here. We're most interested in this first crossing. I mean, technically the first crossing is back here at 0. If we just show this here. So back here at 0, that's where you started this graph, presumably. But then your angle, your r value rather, increases as you draw that petal. And then as you come back to the pole, your r value decreases back to here. So let's find out what this x-intercept is. Let me do second trace option 2 for 0. And let me move my spider a little bit to the left of that intersection. Press enter. A little bit to the right. Press enter. Enter one more time. And that's about 0.4488, which I have down there. And I'm going to call that a special thing. I'm going to call that P, just so I can bring it up whenever I need to and not have to write this number ever again. And I'm actually going to go on my calculator and do that too. So let me quit out of there. I'm going to go to the store button, and I'm going to store that as alpha P. That stores the intersection I just found as P. All right. So now what? Well, now I have to use my area formula. So I'm going to take an integral from one end of the petal to the other, basically what the starting and ending angles, and I'm going to have 1/2 r squared d theta as the integrand there. So specifically, I'm going to have an integral from 0 to p, because 0 and p, those were the places where this petal hits the pole. The 1/2 that I normally have in here, I'm going to pull outside of here. I mean, it doesn't really matter where you put it, but you can pull it outside if you want. And for r squared, well, that's going to be sine squared of 7 theta, d theta. And now to plug all of this in the calculator. So to make this happen, let me take care of my 1/2. So alpha y equals n over d, 1/2. There we go, fancy fraction. Multiply that by math 9 to get integral. We're going from 0 to alpha p. Glad I don't have to rewrite that thing again. And in here, this is really r squared that I'm doing in here. And I stored my r, my sine of 7 theta, as y1. So let me just do alpha trace y1, and I'll just square that, and that takes care of that. And then I'll just put an x here because that's what my input variable is in function mode. Press enter, and that comes out to 0.112, which is giving me answer choice A. For this one, we're going to have to try to explain symbolic notation in terms of other things. So we're told that during the time interval from 0 to 2 pi seconds, a particles moving along a polar curve given by r equals f of theta, so that at any time theta and t are the same thing. So basically you could think of this as f of t. Kind of a roundabout way of saying that, but whatever. The function f is positive, r is measured in inches, great. Which is the best interpretation of f prime of 4 equals 3.2 in terms of the particle? So f, again, this is basically, f is representing the radius, which is essentially the distance from the origin. So this is a change in the distance from the origin, the rate at which the distance from the origin is changing. And they're saying that that's 3.2 is that rate of change. Now, that's happening at the time 4, because we said that theta and t are the same thing. So when I'm doing f of a number, you could think of it as f of some time. So at time 4, then, the distance from the origin is changing at 3.2, whatever the units here are. I guess it would be inches per second. So let's just look at our answer choices and see if anything matches that. So choice A, distance of the particle from the origin is 3.2 inches at time 4. Well, not quite. This would be if you used the original function f and plugged 4 into that and got an output of 3.2. So that's not quite it. We needed f prime of 4. Choice B, distance from the particle of the particle from the origin is increased by 3.2 over the interval 0 to 4. So this would be if you took the integral from 0 to 4 of f prime and got 3.2 back. That would be what's happening here, is the overall change in the distance from the origin. Choice C, distance of the particle from the origin is increasing at a rate of 3.2 inches per second at time 4 seconds. This is what we wanted, the rate of change at a certain time of the distance of the particle from the origin. So this is a big yes. We're going to pick this one in a minute. But let me just look at choice D for the sake of argument. Average rate of change of the particle's distance from the origin is 3.2 inches per second. So this one's a little tricky because it's a rate of change, but this is the average rate of change. That's not what f prime gives you. F prime gives you the instantaneous rate of change. Average rate of change over this interval would have been f of 4 minus f of 0 over 4 minus 0 equaling 3.2. So that's not quite it. So then choice C is our answer. On this problem, I'm just trying to find the slope of the line tangent to this polar curve at this angle. So basically, I need to figure out an expression for dy over dx in terms of theta and then plug in this theta value. And whatever I get out of that will be my slope. Okay, that doesn't sound too bad. There isn't even a trig function involved in this, so how bad can it be? But first, in order to get dy over dx, I need to get y prime and x prime of all this stuff in terms of theta, which means I need to basically come up with a set of parametric equations to describe this. I need to write x in terms of theta, and I need to write y in terms of theta, and then I'll put all that together in the end. So let me get x of theta. That's going to, in general, be r cosine of theta. So in this case, that's going to be 4 theta squared, which is r, times cosine of theta. Now I'm going to have to take the derivative of this because the dy over dx I'm going to use at the end has an x prime in it. To get x prime here, I need the product rule, u prime v plus uv prime. So I'm going to use my box and ribbon to organize all this. I've got my two factors, 4 theta squared and cosine of theta. The derivatives of those are going to be 8 theta and negative sine of theta. Using the ribbon to multiply that out, I've got 8 theta cosine of theta minus 4 theta squared sine of theta. So that's my x prime I'm going to use later on. Now I have to figure out y of theta, and then following that, y prime of theta. So y of theta is going to be r times sine of theta. So 4 theta squared times sine of theta. And to get that derivative, pretty much the same thing I did here. We have to use the box and ribbon, the product rule. So I still have 4 theta squared, but now I've got sine of theta instead of cosine of theta. So a little bit different, but very similar. So we've got derivatives of 8 theta, and this time we have cosine of theta for that derivative. Multiplying all that out, that's 8 theta sine of theta plus 4 theta squared cosine of theta. And now I need dy over dx evaluated at theta equals pi over 4. So I'm going to basically do y prime of theta over x prime of theta. So that's going to be, here's y prime of theta. It's the y prime with theta plugged in for all the thetas, or pi over 4, I should say, plugged in for all the thetas. Too many Greek letters on this one. Down below, I've got x prime of theta with pi over 4 plugged in. So we have 8 times pi over 4 cosine pi over 4 and all the rest of it. And now we just have to simplify it. Now, if this were a free response, you'd actually be done because these are all constants. But because it's not, because you have to match one of these multiple choice answers, you actually have a whole bunch more work to do. Like the calculus really ends halfway through this problem. The rest is just simplifying and unit circle stuff. So let's start with our numerator. Up here we've got 8 times pi over 4, which reduces to, let's see, 2 pi. And then sine of pi over 4 is root 2 over 2. Over here, let's see here, this is pi squared over 16, which we can multiply by the 4 to get pi squared over just 4. And then cosine of pi over 4 is also root 2 over 2. So at least there's not a whole big variety of this unit circle special angle stuff. Down below, we again have 8 times pi over 4, which is 2 pi. Cosine of pi over 4, root 2 over 2. And then this is going to be minus pi squared over 4. And we have another root 2 over 2 for the sine of pi over 4. Still got to keep going because this is not any of the answer choices. To make my life a little bit easier, I'm going to try factoring in the numerator and denominator. I notice that all of the terms in the numerator have a pi and a root 2 over 2 that I can yank out of there. And that'll leave me with a 2. And also over here, I'm going to have, let's see, we still have a pi, and we still have an over 4. There we go. Down below, I can also yank out a root 2 over 2 and a pi, and that leaves me with just 2 minus pi over 4. Still doesn't match an answer choice. We can cancel out these pi radical 2 over 2's here, and then this parentheses here, 2 plus pi over 4, I can think of that as 8 over 4 plus pi over 4, or just simply 8 plus pi over 4. And down here, 2 minus pi over 4, well, I can rewrite that pretty much like up here, except we have 8 minus pi over 4. Getting there, if I multiply by the reciprocal, these 4's are going to cancel. So I just end up then with 8 plus pi over 8 minus pi, which finally matches answer choice C. For this problem, we have the graph of the polar curve r equals 2 minus 4 sine of theta shown up here. We want to know which expression gives the area of the inner loop of this polar curve. So in general, the area formula, we have the integral from a to b of 1/2 r squared d theta. And you can see that in the answer choices. There's some r that's being squared here. And it looks like r in all these cases is 1 minus 2 sine of theta, which doesn't really quite look like this r that they gave us, so that's kind of mysterious. But we'll get there when we get there. The first thing we're going to figure out is our limits of integration, because we have some different options here. 0 to 2 pi, pi over 6 to 5 pi over 6, and some other things. So if I want to get this inner loop, the angle where this inner loop begins and ends, those are going to be the angles where this function is hitting the pole, which basically means that my r value needs to be 0, because at the pole you have a distance from the origin of 0, an r value of 0. So let me start by setting this stuff equal to 0, and then solving for theta. So if I subtract 2 and divide by -4, we can say sine of theta equals 1/2. And I know sine of 30 degrees is 1/2, so is sine of 150 degrees. So then I can say theta equals pi over 6 and 5 pi over 6 if I convert those into radians, which I need to do because, hey, it's calculus. So now we have the integral from pi over 6 to 5 pi over 6 of what? Well, now we need 1/2 times r squared d theta. So I'm going to write 1/2 times 2 minus 4 sine of theta squared d theta. That's great. Unfortunately, that does not match any of the answer choices. It's kind of close to 2 of the answer choices. B and D look pretty good because they at least have the right limits of integration. But now to get a hint on what happened here, I mean, you might notice that, far from having this 1/2 in there, we have something that's not even a fraction being multiplied by this. But the key here is noticing inside that squared parentheses, we don't have 2 minus 4 sine of theta. We have 1 minus 2 sine of theta. It's almost like somebody factored a 2 out of here. But you can't factor a 2 out of this because the whole thing is being squared. What you could do is factor out a 2 squared. You can think of there as being 2 of these 2 minus 4 sine of theta parentheses. So if you want to factor a 2 out of this, you need to factor a 2 out of both of those parentheses. So I factor out a 2 squared from all that. That allows me to leave this as 1 minus 2 sine of theta, the whole thing squared. But now what is 2 squared? That's just 4. What's half of 4? Oh, that's just 2. So I really just end up with 2 times all that stuff squared. And that, at long last, is going to match answer choice B.